Let's do some trig, shall we? We want to find the exact value of the trigonometric function at the given real number in the first set of problems. These ones right here. Now, it's no coincidence that these happen to be the same number over and over, this negative pi over 3 thing. This is chosen from a problem set where, you know, it's just the same position over and over, and then you switch positions, you take a bunch of functions of those. But we are going to see how to solve this even if the number kept on changing. Because in general, what you do is you draw a unit circle, which of course is a very nice circle because I'm perfect. No. Negative pi over 3. If you're still in the point where you're converting radians into degrees, you can think of pi as being 180, divided by 3 is 60. And it's the negative direction, which means that we're going to go this way. So this is negative 60 degrees. You don't have to do that conversion. If you just know that that's where it is, then that's awesome. So it's right here. You can consult your standard unit circle and find that this position is the same as the 300 degree or 5 pi over 3 position. You could also just draw a 30, 60, 90 triangle and get that it has the coordinates 1/2, comma, negative root 3 over 2. So this lets me say that the cosine of negative pi over 3 is the x coordinate of that point. It's going to be positive 1/2. That one was easy. Number 1, taken care of. Secant of negative pi over 3. I could dig into this and do the whole like x over r and then like flip things around. However, I also know that this will be 1 over the cosine of negative pi over 3. And I just found that. So there's no reason to get fancy here. This is going to be 1 over 1/2, which is 2. Both of these have been taken care of. Now I need the tangent. Okay, the tangent, I only have room up here. So I'm going to do it at the top. Tangent of negative pi over 3 is the sine over the cosine. Sine of negative pi over 3 divided by cosine of negative pi over 3. This seems like it makes things worse, but remember that the coordinates on the unit circle are precisely the cosine for the x coordinate and the sine for the y coordinate. So I'm going to put in the negative root 3 over 2 as the sine, and then put in positive 1/2 as the cosine. This turns into reciprocal multiplication, keep change flip if you call it that, negative root 3 over 2 times 2 over 1. The 2's go away, and this ends up being negative root 3. So all 3 of these are taken care of, just with drawing that single diagram. If you had to do more than one position, draw a new diagram for each position to make it easier on yourself. Okay, one more question before we're done for today. It's this one. The terminal point of an angle contains the point 40 over 41, comma 9 over 41. Find sine, cosine, and tangent. All right, let me give myself some room here. (40 over 41 and 9 over 41. Well, honestly, this is a little weird. What I'm going to do is times this by 41 and get that it's along the same line as 40, comma 9. So 40 and 9, like right there. If you know anything about trigonometry, which hopefully you do, you know that it doesn't matter whether you do the trig function at that point or that point or that point or that point, because they're all similar right triangles. So I can actually take these inconvenient numbers and turn them into ones that are easier to deal with. Hence the multiplying by 41 to get 40, comma 9. It's going to have the same trig values as the original. So 40, comma 9 is now easier to deal with. And let me see. This right here is 9. This is 40. What is this? Well, I have to do a squared plus b squared equals c squared. This is going to be really nice, though, I promise. 9 squared plus 40 squared equals c squared. 81 plus 1600 equals c squared. 1681 equals c squared. This is 41 squared. To see this, think of this. 41 times 40, and then plus one more copy of 41 is the same as 41 times 41. 41 times 4 is 164, and then tack a 0 on the end. Plus 41, that's 1681. So this right here means that C is equal to 41. This actually is one of your special triangles. It's, like 3, 4, 5, 5, 12, 13, 8, 15, 17. This is another one, the 9, 40, 41 triangle. It's pretty obscure. I'm not sure that you've heard of it. Only cool guys like me get to know about these triangles. But it is another one where you don't have to have messy square roots in either of the legs or the hypotenuse. We want to get sine of t here. So sine of t, in this case, it's better to use the y over r definition of sine. Y over r, which in this case is 9 over 41. And cosine of t is the x over r, which is 40 over 41. And tangent of t is equal to the sine over the cosine, or the sine times 1 over the cosine, right? So the sine of 9 over 41 times 41 over 40, that's 1 over the cosine. 41s go away, and we get 9 over 40. Now, I do want to make one last comment about this, because I'm guessing you noticed that these two are actually the original coordinates here. And you might be thinking, well, what the heck? Wouldn't there be an easier way to do this if the sine and the cosine were already given to us? Well, only if you recognized that those points were on the unit circle in the first place. Because guess what? We scaled the whole problem up by a factor of 41 from the start, right? Yes, that was how we turned them into nice numbers. But if we scaled the whole thing up by 41, that means that going back to the original problem, like going way back down to here, if we took this radius now, say that this is actually 40 over 41, comma 9 over 41, then scaling it down by a factor of 41 means that that radius is 1, which means that this point is actually on the unit circle, in which case it shouldn't be surprising that the x-coordinate is the cosine and the y-coordinate is the sine. Of course, that would be pretty hard to notice from the get-go. So super extra points if you already knew that from the start.